Hello, this is a presentation of the paper Interpreting Intermediate Convolutional Layers of Generative CNNs Trained on Waveforms by Gasper Begush and Alan Joe. So interpretability is one of the main frontiers in AI research, but most of the work focuses on the vision. We here claim that for interpretability, spoken language is a much better testing ground because it's simpler and more interpretable. If you think of how many colors and shapes there are in the visual world, it's many, but human languages usually have a couple of dozen phonemes. And so simplicity is important when we're doing interpretability work, when we try to interpret how these models are learning. We claim that humans perform precisely this discretization that neural networks need to be trained on as well, which is they take some continuous space, for example, sounds of spoken language, and turn them into discrete representational units, which we call phonemes. And we've been studying them for decades, if not centuries. And we have a very strong understanding of the data we're studying, unlike maybe in the visual world. And so we have complex processes, we have more simple processes, and we can use those to basically interpret how the models are learning. And also our generative data in humans, right, is easier to access in spoken language than in vision. We constantly produce speech, and it's very easy to record that speech versus much more difficult to record human imagination, or like how we imagine images in the brain. So we propose a new technique to interpret and visualize intermediate layers in generative CNNs that are trained on raw speech in an unsupervised way. And this technique basically allows us to test how and where any acoustic property is encoded in convolutional neural networks. And we combine this technique with a linear interpolation of a model's latent space to show a causal relationship between individual variables in the latent space that have some linguistic meaning and activation in models' intermediate convolutional layers. So what are the advantages of the new proposal? So because we're manipulating and interpolating individual latent variables well outside of training range, we can basically observe the causal relationship between something that the network encodes as meaningful in the latent space and intermediate representations in convolutional layers. We can test any acoustic property, how they're encoded and in which layers via correlations. And we're not testing only acoustic property, but also phonological processes. And this is going to be important as the speech technology is becoming more available in languages with more complex phonologies than English. Our models are fully unsupervised, trained on raw speech, and we require no further processing of the output. So no further transformations or PCA analysis are required. We're basically looking at raw data. So we take a 5-layer convolutional layer generator and analyze an internal representation. So most previous work focuses on filters. We focus on feature maps. But if you just look at the feature maps, these are a few convolutional layers and all feature maps there, they're not very interpretable. And so that's why we propose that if we average over all feature maps in each layer in the time domain, we get a very interpretable summary of what each layer encodes. For example, purple is the output, an STV SPA-like sequence. And orange you see is the previous layer, the fourth convolution layer. Green is third convolution layer, and we can basically analyze what each layer encodes, and we get a time series per each layer, which could be treated just as if it's an acoustic property, acoustic signal, right? Here we have an example of how a vowel is encoded, right? So purple is output, orange is fourth convolution layer, green is the layer before that, and we see at each layer what information the network encodes. This is frication noise, for example. We can analyze correlations between output and intermediate convolution layers to see where and what is encoded at which layer. We can test F0, intensity, or any other property. And as I mentioned, we don't know. Not only we basically get a summary of what each individual layer is encoding, we can also get a causal understanding of what intermediate layers are doing. Okay, so we can find individual variables in the latent space that encode some meaningful property, for example, the presence of S. And we can interpolate, basically forcing S in the output by interpolating a single latent variable, for example, 11th latent variable. As we're interpolating it outside of training range from 0 to -15, we see that S in the STV sequences starts appearing and increases in amplitude. In the fourth convolution layer, this is pretty faithfully encoded, right? So this is frication noise that increases, and we have silence corresponding to the stop and vocalic periodic vibration corresponding to the vowel. In the layer before that, things are more abstract and more abstract, to the point that the first layer, we basically only get 4 spikes of activations. Now, as I mentioned, we can test simple things like the presence of a phoneme, or we can test complex things as well, like a reduplication, which is one of the most complex processes in phonology, morphophonological processes. And we can see how through the layers, something like a single unreduplicated monosyllabic word gets reduplicated into something like from the die to the die with a disyllabic reduplicative syllable. And we see how the generator basically starts in the deepest layer, just sets the low frequency processes like acoustic envelope, and then adds information as it moves through the layers. So we argue that lower frequency properties, such as acoustic envelope, are encoded in earlier convolutional layers, and the properties with higher frequencies get added on top of the envelope in later layers. Our technique also allows us to analyze individual individual feature maps, and we can do interpolation and causal exploration there as well. Okay, so to conclude, we can analyze which acoustic properties are encoded in which intermediate convolutional layer, and that basically gives us an understanding not only how phonetics how acoustics is encoded, but also how phonological processes or processes as complex as a reduplication get encoded. And we basically explore a causal relationship between individual latent variables and representations inside in the intermediate convolutional layers. Further directions, there are other acoustic properties that can be explored or tested with this technique. For example, acoustic correlates of gender, dialect, race, or socioeconomic background. The technique can serve as a diagnostic to improve performance of convolutional neural nets, and it gives us a way to compare the brain and the artificial neural network. So it gives us a really interesting insight that allows comparison of speech correlates in the brain and speech correlates in artificial neural networks. Thank you.